What's up, everyone? This is probably my first number theory problem in my channel. So today we're going to find all n in this set such that n to the fourth power plus 4 to the nth power is a prime number. Now, most people probably already know what this symbol means. It is the natural number. But sometimes people will argue that should we include 0 or not in the set of natural number? Well, personally, I would not include 0 as part of the natural number. And if I have to denote the natural number sets including 0, I will probably put the not right after the symbol of natural number. But in this case, it actually does not matter. And we will see why. So let's jump into the solution. Okay, so let's try to find some numbers and observe if there's any patterns or not. So regardless if we include 0 or not, we'll actually end up with the same result. So let's start with n equals 0 case. So if n equals 0, we get 0 to the fourth power plus 4 to the 0th power, which is equal to 1. Now remember, 1 is not a prime number and is also not a composite number, meaning that can be rewritten as the product of 2 or more non-primes not equal to 1. Okay, so clearly the case n equals 0 doesn't work. Next, let's observe n equals 1 case. So if we substitute in, we got 1 to the fourth power plus 4 to the first power. And 1 to the fourth power is, well, of course, 1 to any power is 1 if we have an integer. And plus 4 to the first power, well, that means there's only one 4. We're not going to multiply anything else. So we get 1 plus 4, which is equal to 5. And of course, 5 is a prime number. So n equals 1 case actually works. Okay, so let's see what happens if we choose n equals 2. Well, if n equals to 2, we get 2 to the fourth power plus 4 to the second power, which gives us, well, 2 to the fourth power is 16, plus 4 squared, which is also 16, which is equal to 32. And since 32 is an even number that's bigger than 2, obviously this is not going to work either. How about n equals 3? Well, if n equals 3, we get 3 to the fourth power plus 4 to the third power. And 3 to the fourth power is 81 plus 4 cubed, which is 64. If we add them together, we get 145. And since we have a multiple of 5, which ends with 5, but is bigger than 5 itself, clearly 145 is also not a prime number. So if we keep listing, we probably might find a pattern that looks like n equals 1 is the only answer. And for n is bigger than or equal to 2, we will somehow get a composite number. So how are we going to prove it? Here's what we're going to do. So here comes our actual proof to show that n equals 1 is the only solution for our problem. So first, we're going to separate this into 3 different cases. Let's show that n equals 1 is going to work first, which is the easiest case. When n equals 1, we get n to the 4th power plus 4 to the nth power equals, well, substituting in, we get 1 to the 4th power plus 4 to the 1st power, which is equal to 5, which is a prime. So far so good. We already finished one case. Now, what happens if n is an even number? Then let's do a replacement. Let n be equal to some 2k for k is an integer. Well, actually in our setup, it will be the natural numbers. And again, we have already seen that the 0 case is not going to work either. So here we don't even have to worry about it. Then what do we get? Well, we now get n to the 4th power plus 4 to the nth power equals 2k to the 4th power plus 4 to the 2kth power. And remember that k in this case is a natural number that is bigger than or equal to 1. So obviously, we can claim that this is even and this is also even. In fact, we can now try to factor out a 2 from both terms, giving us 2 times the quantity, 8k to the 4th power, plus the other term, which is same as 2 to the 4kth power. So if we factor out a 2, we get 2 to the 4k minus 1st power. Okay, and as k is bigger than 1, this term is bigger than or equal to 8, and this term here is bigger than or equal to, let's see, k, the smallest k we get is 1, so we get 4 minus 1, which is 3, which is also greater than or equal to 8. So altogether, it means that this term is greater than or equal to 16, which is clearly bigger than 1. And since this is a product of 2 integers greater than 1, it means that this in our case, when n is even, this is not a prime. Is not prime. All right. Well, since the board is already filled up, I'm going to erase it and then finish with the last case. So from the last board, we already found that n equals 1 is one of the solutions, and for n equals any even number, we get no solutions for our problem. So For our last case, we're now going to assume that n is odd. We're of course not including the case that we already found, which means n is greater than or equal to 3. We can suppose that n is equal to 2k plus 1, and again k is some natural number. And how's this going to help us? Well, let's substitute in and see what's going to happen. So n to the 4th power plus 4 to the nth power is going to be equal to 2 to the kth power, 2k plus 1 raised to the 4th power plus 4 to, let's see, 2k plus 1st power. Now, let's see what we can do. Well, we're going to do the following. Here, we will keep the first term the same, and we're going to use a trick called Sophie-Germain's equation, which is saying that we are now going to break the second term into 4 times 4 to the 2kth power, which in fact is the same as saying 2 to the 4kth power. And next, we're going to add something. And of course, since we're not doing equation, we're not going to add on both sides, so we need to eventually add a zero term. But this time we'll get a fancy zero term, which looks like this. We're going to add 4, let's see, we're going to add 4 times 2k plus 1 raised to the 2nd power, which, if you might notice, we're taking the square roots of this term here plus, well, not plus, multiply with the square root of this, which is 2 to the 2k power. And of course, we need to subtract the same thing so that we're not adding extra stuff in our expression. And how is this going to help? Now we see that the first line is in fact a perfect square, which can be written as 2k plus 1 raised to the 2nd power plus, well, if we look carefully, putting this in the middle, we will actually get a squared plus 4ab plus 4 times b squared. So if we take the square roots of this whole thing, we get 2 times 2 to the 2k. Well, or we can combine it back as 2 to the 2k plus 1st power. All right? And now we complete the square from the first 3 terms. And notice that the remaining term here is also a perfect square if we ignore the sign. Which means now we can write the second part into, well, if we take the square roots, we now get 1st power, 2k plus 1 to the 1st power, times 2 to the 2k, square root of it is 2 to the k power, times another 2. So we have 2 to the k plus 1st power. And we have the whole thing squared. So now we have the difference of squares. We can factor it out, get the following. Okay, so this is what we get after we factor out. So again, since n is bigger than or equal to 1, the first term here the first factor is clearly bigger than 1. Now, let's take a look to the second part. Can we somehow show that this is always bigger than or equal to 1? Well, in fact, we can do that because we can just try to list some of them out and see when we will get the smallest value. And I believe no matter how small the value we'll get, we will still be able to get bigger than 1. Okay, and I'll leave this as an exercise for you guys to check that part. So now we see that this expression can be written as the product of two integers that are bigger than 1 when n is greater than or equal to 3 and when and n is an odd number. What does this mean? This means that this is a composite number, or in other words, it is also not a prime number when n is bigger than or equal to 3. Therefore, we jump to our conclusion that the only possible case that the expression n to the 4th power plus 4 to the nth power is a prime number if and only if n is equal to 1. And that's it for our video. If you think this is cool, don't forget to like. And if you want to watch more of my videos, you can subscribe and turn on the bell. Yeah, you can subscribe and don't forget to check my check out. Okay, that's it. So pretty cool, huh? If you think this video is interesting, don't forget to like. And if you want to check out more of my videos, you can subscribe or go to my channel and you will find out other videos. So that's it. Thank you for watching. I'll see you next time.